Okay, this is the first time you've seen this, the study of calorimetry. And you may notice the similarity there in the word calories, about heat energy. When you think about calories in food, it is also calories, it is about energy, but the difference is that a calorie we're going to talk about in chemistry is a little bit different than the units you see on a candy bar. So if you look at an item of food and it says, oh, that granola bar, one granola bar is 100 calories, okay? It is 1,000 times more than a calorie in chemistry. So I think they do that because if you looked at that candy bar, that granola bar, and saw it was 100,000 calories, you might not eat it. But that is the difference. Calories for food are 1,000 calories for each one in chemistry. Okay, so calorimetry, the study of heat transfer, the study of heat moving from one thing to another. Remember from last year in physics that we cannot create or destroy energy, and that means since heat is a type of energy, it cannot be created or destroyed. We can only move it around. Heat is energy. Remember when we started at the beginning of the year talking about molecules and motion, when we had more heat, we had more motion. So as we heat things up, we make molecules move faster. Energy can be transferred or transformed, but in this case, all our heat energy is going to stay heat energy this year and for the next month and a half. Energy is always going to stay as energy. We're going to use the symbol Q, lowercase q. That's the symbol for heat energy. And what that Q equals, negative Q. And you're saying, wow, my math teacher wouldn't like that. What that really says is the heat lost from one system or item or object has to be gained by another system or object. So as Fred said right at the beginning, if you have a hot cup of coffee and it loses 10 joules of energy, the air around it, a different system, must gain that same amount of energy. All right, so how do we actually do the calculation? We use three things. M for mass, the mass of whatever it is that we're looking at. Could be the mass of a cup of coffee, the mass of a volume of air, specific heat, the letter C. These are determined through experiment, and we can look them up on the internet or look them up in a book. So we call them book values. For our purposes here at the beginning, I will be providing you with what the specific heats are, but you can look them up. These are not to be found on a periodic table because we have specific heats for molecules as well as elements. And delta T, the change in temperature, remember we talked about final minus initial. All right, so let's go ahead and do a calculation. So to do this first one, I'm going to switch over here a little bit to do some work in the iPad, but calculating heat energy. How much energy, letter Q, is needed to increase the temperature of 100 grams of water from 20 degrees Celsius to 35 degrees Celsius? And I'm going to tell you the specific heat of water is large. It is 4.186. So our equation, Q, the energy, heat energy, equals M times C times delta T, the change in temperature. So we're just going to fill in some numbers. Energy equals the mass, so 100 grams, times the specific heat of the water, 4.186, times the change in temperature. We're going to go from a beginning temperature of 20 degrees Celsius to a final temperature of 35. So it's temperature final minus temperature initial. And if you do that calculation, it will be 6,279 joules. And we're going to be working with joules for right now. So that's how we do that calculation.